So let's look at some applications of saddle point asymptotics to combinatorial problems. So one problem that we saw very early on is that we can write down generating function equations for the number of permutations that have no long cycles. So in the simplest case is involutions where all the cycles are of length 1 or 2. So immediately from the symbolic method, we get the generating function for involutions is I of z equals e to the z plus z squared over 2. That's a function that's got no singularities, and it's immediately amenable to the saddle point method. So we have e to a function. All we need to do is take the derivatives of that function, set the first one to 0 to find the saddle point, and then that's the function. We take z plus z squared over 2, then minus n plus 1 log z because of the z to the n plus 1 that we put in for Cauchy's formula. Saddle point is where the first derivative is equal to 0, and so that turns out to be a quadratic equation in this example, and it's about square root of n minus 1/2. Again, we want to work with approximation to the saddle point to simplify calculations, and so then the saddle point approximation says that we plug that square root of n to the n minus 1/2 into the original equation, and that immediately gives the saddle point asymptotics. E to the square root of n plus n over 2 minus 1/4 over 2 n to the n over 2 square root of pi n. That's kind of a complicated equation, but that's the asymptotics for this problem. Actually, we're interested in factorial times that coefficient, so just plugging in Stirling's approximation gives that asymptotic expression for involutions. Fairly straightforward calculation using saddle point asymptotics. Now again, you have to check susceptibility or give up on the square root of 2 pi n factor. Here's another example, set partitions that we looked at. How many ways are there to partition a set of size n? From the symbolic method, we immediately get e to the e to the z minus 1. That's immediately amenable to saddle point. We start with ez minus 1 minus n plus 1 log z. So our saddle point is where e to the zeta equals n plus 1. That's at about log n minus log n. Now that one you can plug in, but you get a fairly complicated, complex expression. And just since we're near the end of the lecture, just look at the bound. The bound says just plug in g of zeta over zeta to the n, and you see that it's about n over log n to the n is the saddle point bound for this problem. And we could get rid of the square root of 2 pi n factor with some work and some basic asymptotics. But as is illustrated by so many of these problems, maybe using the bound is a good place to start. So there's many combinatorial applications. So we looked at e to the z, which is generating function just for erns, and central binomial or Catalan, and involutions, and set partitions. I didn't go as far as doing the coefficient asymptotics. There's a few other examples in the book. But definitely some of these calculations are quite complex, and it would be more in advanced analysis. So I'm not going to claim that the saddle point asymptotics is as simple a transfer theorem as we saw for many other examples early on. But still, this places the whole idea in context and illustrates that we do have approaches to cover all the generating functions that we can get from this symbolic method. That's applications of the saddle point method.